GitHub recently, in the last week or so, which is owned by Microsoft now, has put out this new a preliminary version of something called GitHub Copilot, which, well, let me just, I'll just play this for just a second here.
Lines of code that you want today, because artificial intelligence is coming to a PS code near you. Microsoft.
Is everybody online able to hear that?
Kind of muffled.
Kind of muffled. All right, let me see. That should be.
GitHub just announced Copilot yesterday, a tool powered by GPT-3 capable of writing code automatically. All you have to do is write a descriptive function name or some comments, and it will automatically fill in implementation details for you. And it's not just inserting a snippet, this is actual novel code that has never been seen before. It looks at the code you've already written in your project as context and attempts to generate new code to match it perfectly. For example, imagine you've written a React component and you now want to write a unit test for it. Just write a comment describing what you want to test, and Copilot will generate the code based on your component and the testing framework that you're using. Or say you want to calculate the number of days between 2 days. For me, that's an instant Google search, then Stack Overflow, copy and paste. With Copilot, all I have to do is write a function name, and it implements the function body for me automatically. If I'm not perfectly happy with the implementation, I can click a button to get the next prediction. Anything that might have brought you to Stack Overflow can be auto-configured in your IDE.
Okay, so I'll let folks online kind of Google it so they can watch it at your own leisure, and everybody in class can check it out. It's sort of inevitable that everybody's going to know about this thing. So there's all sorts of interesting things. Basically, my understanding of it is, and I haven't gotten to try it yet, but what GitHub now, this GitHub Copilot kind of add-on to Visual Code or Visual Studio and lots of other tools potentially, they're mining all of the publicly shared code on GitHub. So if you've posted a GitHub repository that has been marked public, it has potentially been read and sorted and cached, and statistics have been drawn from it, and so on and so on and so on. So that now, using GitHub Copilot, you can basically, you could imagine, say you were writing an OpenGL program, and you tried to write a function called setupCube. It would sort of go through every other, or it has already gone through every other OpenGL program out there written in C++, because that's what the language you've told it about. And it'll look for things that it can kind of relate to setupCube. So it would go and find my code, the sandbox code, and see that in there, or set up quads and so on and so on. So it would probably try to set up a VAO and a VBO and do the right things and all that, because that's what most people do. So some of the interesting things, like in this slide, also they claim, or they're saying that it generates novel code. So it actually doesn't just copy and paste either. It will be context sensitive about where you're putting it in, where it came from, all that sort of thing. And you can ask for multiple variations. You can kind of step through the ones that you like. I've seen demonstrations of it where you could start to type a comment after putting a certain piece of CSS code, and suddenly we're like, oh yeah, 90% of the time people say, oh, I'm setting up a button here, or I pulled this from the DOM here, or something like that. And it would find those comments and just paste those in for you. If you look up GitHub Copilot crushes LeetCode, one person stacked it up against the LeetCode standard interview questions, certain algorithms and things, and it was just, every one of them that I saw, it was able to find, some sort of context and find good answers and all that sort of thing. So it's amazing and terrifying, and it's going to potentially change a lot with regards to the computer science field. I suppose less the computer science field and probably the coding field, the programming field, sort of because it's not, it's sort of the science of it, right? It is, I suppose, in the same way that it should shake up medicine, the way AI can shake up medicine by finding and making all these connections and making suggestions and so on. We're gonna, the computer science is gonna eat its own dog food, as they say. It's gonna live or die by its own sword. So challenging for things like, well, okay, I need an algorithm, I just go and grab it. You know, if you have a description of something you're doing for your homework, or, you know, setting up a cube or an off-screen surface, or you know, implement this depth first search or whatever, if you have this installed, you're just going to put it in and it's going to like find good versions, and you could, you know, have it do variations and that sort of thing. So potentially it cheating on homeworks, yeah, okay. How would you detect it? You know, ultimately, you know, you have to ask, I suppose, from the education point of view, we'll have to like ask a lot more questions about why you think it did that, or, you know, why does this code work? What is, you know, what are the concepts behind it? You know, demonstrate things, talk about things, have discussions. Far less relying on more, you know, submittee style auto grading and so on. Because if we just do that, well, you know, this could certainly make life really challenging to evaluate people's work. But also, that part aside, you know, the challenges on the education aside, the challenges in computer science, this sort of trivializes the need to then, you know, memorize every algorithm out there. You know, so if you were someone in the field who just prided themselves on, you know, yes, I've memorized every algorithm out there, congratulations, you compete with Copilot. And, you know, the question is, as people in this field, how are we ultimately going to compete with AI like this? You know, it's the same way that people compete with all sorts of other automation and so on. And I think it's amazing. The potential is great. Like, imagine for the independent software developer, or the indie game writer. We had a little discussion before about this. Potentially really cool, because you could say, well, all right, I'm just one person. Now I can mine all of GitHub and whatever I need, some kind of, you know, collision detection thing, or I need to implement a inventory system in Unity, and, you know, its ability to visually design things. I'm sure it doesn't have any of that yet in there, but certainly back-end stuff is going to be pretty amazing. So it's, I don't know, I predict that it potentially, you're going to see more and more about it. You're going to hear more and more about this thing from all sorts of different angles as, you know, an amazing tool and a fierce or terrible weapon or a crutch. I've already seen some discussions with regards to, well, what about open source? And, you know, how do you acknowledge where the code came from? I mean, that's one of the things I like to do. I ask for students, you know, hey, it's okay if you cut and pasted and things and so on, as long as you give attribution to where code came from. You know, tell me that you got it from somebody else who implemented it in this really cool way, and, you know, tell me how you understood it and so on. Everything I've seen from GitHub Copilot so far, it generally just, you know, searches, found it. You know, it doesn't tell you where it got it from, doesn't tell you how it came up with it. So there's a lot of people who are concerned about, you know, licensing and ownership and attribution and so on and so on. You know, just declaring something to be public doesn't necessarily make it open source, or, you know, under a certain license. So there's lots and lots of issues like this. I wish I was teaching an ethics in computer science course or something like this. I have to talk to Professor Hendler, who just Professor Hendler is now, he was, or is the head of the ACM policy committee globally now. So the ACM is the Association of Computing Machinery, something like that. They talk all about ethics in computing and all kinds of different things. This is bound to be on that list. So I'm very, very curious to see where this goes. And in terms of this class, what does it mean? Why do I want to talk about it? Well, I guess this sort of reinforces my feeling that just giving sort of simple coding challenges only goes so far, because you can just kind of find that stuff online, and that's all well and good. But ultimately, it's how do you put it into practice, and what do you do with it, and so on. So thinking about the projects, and I haven't actually posted grades for all the projects yet because we're still some of them in a state of flux. I wouldn't say turmoil. But my general feeling on them, everyone who showed something last week is probably, we'll just say we're looking at the 90 to 100 range. I think everybody is, everyone should feel really good about the projects that they showed. And generally, where everybody is in the course right now, I think you'll find in a lot of the courses that I'm involved in, as long as you're putting in the effort, you're trying, and you're showing progress and so on, you're in the B to A range, and I think everybody, probably right now, and I'm not saying to slack off or kind of use this as a reason to just like kick back and you're good to go. Certainly, everybody can lose an A from here if everyone can at least float down into B range if they tried. But I think everybody is in likely an A and B range right now. Probably more in the A range than the B range. But, that's kind of the fact of it. So I should wrap up my soapbox, I suppose. The big thing is just, I like to see people's efforts. I like to see people's understandings. I like to see people's demonstration of what they're doing. I like people to, if they're having a problem with something, approach me, and people have been doing that. And I just want to continue to stress that. Because things like this sort of just make getting the code just perfect, that makes it different, I suppose. And we're heading in that way. And the sooner we embrace that idea and kind of learn what the new state of the world is going to be, the better. So, all right, that's the end of that soapbox and kind of where we are grade-wise and everything. There's still a few things coming in. We'll have to sort of decide on one of the things. We'll go to content and look at the syllabus for just a moment. Today is sort of the reboot day. The day after a long break always is, to me, a reboot day sort of thing. So it's also just about half the semester, so that's good. I'm always nervous that everything is slipped away from us and we didn't get to cover everything, and we're, oh my God, where are we? But I think we're actually in good shape. We've discussed all the basics. Everyone's showing a pretty good understanding of the basic kind of stuff in OpenGL. We know, if I ask what's a VAO, what's a VBO, how do we pass things to the renderer? How do we what is a texture? What are we typically using textures for? What are the basics of lighting? That stuff we've got that under our belts. So we're in pretty good shape. I think from here, certainly everyone has a pretty good appreciation of OpenGL. And the nice thing is that most systems, even as you get into Vulkan and Metal and kind of newer systems, they're building on those fundamentals. So we're in pretty good shape. Things, for the most part, after this point, we're going to get into, for lack of a better term right now, I'll call them sort of eye candy. All right, we've got the basics. We have geometry. We have shaders. We know what those are. Now, let's get fancier. Let's get trickier. Let's do different things to kind of more precisely or cleverly perform certain types of operations or make them work on the screen. And there's lots of underlying algorithms and mechanisms and things to do these things. And for each one of them, there's at least 6 ways to do it, if not more. And you just plug it into the Copilot, and it'll suggest a whole bunch of them, I'm sure. So let's see where we're at. So I have a couple of things prepared for today to talk kind of about the shadow mapping, which we talked about a little bit last week, and also some of the advanced shaders stuff. We do have on the schedule a homework for Thursday. I'm going to go ahead and push that out. I'll probably assign it on Thursday, and it'll be due at some point next week. So it'll probably be over the weekend type of thing. And also what we have coming up is, in the short term, is this final proposal. And the question there, the final proposal, is really the final project proposal. Do you want to take your current project and build on it? Use some of the techniques that you see here. some of the things I'll introduce within the next really 2 days. A lot of it is going to be shadows and advanced shaders. We'll talk a lot about stuff you can do there. You'll see some of the other things as we get into geometry, shaders, 3D textures, noise maps, fog, and all those. There's sort of specific examples of kind of using shaders in interesting ways, and you'll be able to find even a lot of those if you go to our standard go-to sites, our Learning OpenGL, OGL Dev, OpenGL tutorials, and you can find any number of different uses of those that you can kind of try things out if you want to include those in your final projects. So this week we'll definitely kind of wrap up if anyone has any stuff. And I talked about doing another presentation. I don't think we're going to do another presentation for all the projects. Everyone did fine. If you haven't done a presentation at all, I would like you to prepare a video or something for that. But what I would like, since some of you I think have made some improvements, is just to do basically some screenshots and things and kind of show where you're at. We can share them on Discord. This way everyone can kind of see. That was my big concern. I wanted everybody to see what everybody else has been working on. So I'm going to encourage you to put some screenshots or some short video captures and stuff like that on Discord for people to see, and that I can refer back and kind of home in on the grade for your project. If it's a 88 or it's a 98, sort of thing. We'll shoot for that range, possibly. All right. So how does that sound? Is that vague enough for everybody? It's a little vague, but again, that's why we got to prepare for vagaries, because that's the one that Copilot can't handle, right? So we have to learn to deal with vagary, and the better we are at that, the better off we're going to be. So, okay. So one other thing that I put out there, and let's see if it still runs after having gone through multiple reboots. One of the key techniques that I mentioned last time we were together, and is one of the things that didn't expect to see in any of the current projects, but is a technique that becomes important for a lot of potential things, is the use of off-screen buffers or rendering to textures or kind of doing multiple passes on images and so on. So that's one technique I wanted to at least throw out some specific sample code to kind of start some ideas on there. So I released this, or a slightly more stable version of this, on GitHub. So Copilot, I'm sure now will be able to help you out. Well, I don't know. I could totally kick back and rely on Copilot all the time now. But this is up there. I posted a link to it on Discord, and this should look similar to where we were last time. We had our basically sort of particle cubes. They're all fixed. They're just out there. There's lots of instantiated cubes, lots of instances of our shiny RPI cube. It has a skybox in the background. It has environment mapping on our shiny cubes, and there is some ADS lighting. It's kind of all in there. And so what's the difference? Okay, so the one difference that this demonstrates is there's this checkbox up top, and it says Use Off-Screen Buffer. And if I click that, you'll see two things happen. We now have an inverted version of our scene here down in the IMGUI window. Right. IMGUI supports images, so you can have image-based controls. So what's happening in this version now is the scene, we set up a frame buffer object, which isn't incredibly complex. Set up a frame buffer object, and we render to that instead of rendering to the screen as normal. So that becomes an image that we can share with IMGUI, and IMGUI draws it in here. Now, unfortunately, the way that IMGUI kind of expects it to come in is it expects it to be as if you loaded it with STBI in its normal state, not the swap for texture. So it does wind up looking upside down. That's one odd thing about it. And you also see over here in the background a slightly odd version of the project as well, because what this is actually not the live scene either, but instead is yet another pass that basically does a textured quad using that same texture, right? So we're just showing, we're passing the image to IMGUI in IMGUI's window, and in the other normal, where we put our normal image, we actually are using that generated texture as a texture to then put on a pair of quads. So why it looks kind of funky there is because that is actually being subjected to further environment and lighting and so on. I just did this is using reusing the same shaders over again, which is why it's sort of a little bit odd and broken, right? There's not, ideally this shader that's being used for our image back here, this one here for those online, ideally that shader would be a lot dumber than this version, right? We'd have a dedicated shader that all it did was copy pixels from the texture to the screen and not bother doing lighting, and you'll see like it's actually taking the resulting texture and then adding the environment color to it, which is why you can kind of see that kind of stretched environment in the background. Kind of weird. So this sample is out there, and we can turn it, click it back to normal. Let's see it go back to its normal thing. And I've tried to sort of compartmentalize the code a little bit here. I'll kind of show you where it's at. If we look in our main routine here, we have our typical, should look pretty normal. We're setting up GLFW, we're setting up GLAD, and one new thing is we have a setup frame buffer. And setup frame buffer sets up our handy off-screen frame buffer, right? Generates a frame buffer, which is a new object for us. And then it says, okay, we're going to attach a texture to that, and we're going to use this what's called a render buffer object to handle the depth and stenciling, since we're not going to use those for anything other than the normal scene. You have your choice of doing things sort of as you're rendering off-screen objects. You can either render to textures or to render buffers. So render buffers tend to be faster because it's assuming you're not going to read them and really use them for other things. Whereas textures, you're going to wind up kind of reusing. So you take a slight performance hit by rendering to textures versus rendering to render buffer objects. So sometimes in your applications, you'll see a combination of these in use. So that's kind of what's going on in this bit of code here. And you'll see this GL bind frame buffer. It sets it back to 0. So it's swapping between the default frame buffer, which is frame buffer 0, and the one that we set up here, our magic sort of frame buffer for when we're rendering off screen. So we have to use the normal frame buffer for IMGUI and our quad, but we use our special off-screen buffer for our rendering our scene off scene. So that's where we set things up. That's in our setup frame buffer. Everything else is pretty normal. Going through here, we even have our own vertex array. Everything is, as it was. I added in the actually newer version, I don't think it's the one that's on there, this setup textured quad. The one that I think I last left up is strictly the IMGUI texture version. This just added one bonus thing. I'll put this up. And inside of our render loop here, right, we always look for while GLFW should window close, or window should close. This is our rendering loop here, where it's just iterating over and over again, drawing our geometry, rendering it off screen, updating IMGUI, etc. All those things that need to happen over and over again. So within there, you'll see the first thing it does is it decides in here to, if you're rendering off-screen, right, if our off-screen button is pressed, and for this we're just using a simple Boolean that IMGUI takes care of, right? So this is just a global for off-screen. that IMGUI is, if we look up in, where's IMGUI here? IMGUI now has this wonderful off-screen checkbox, right? That's the nice thing about IMGUI. You want to add a new control, boom, just do that. It fills in the value. So we're going to go down here. If that's checked, it decides to activate the off-screen buffer, and everything gets rendered to that off-screen buffer. All of our other code in here basically doesn't change much, right? This is why it's the simple naive case, right? After it draws everything on here, it does check to see, all right, are we in this special off-screen mode? In which case, well, we want to make sure to turn it back because we don't want IMGUI rendered off-screen, and we don't want our textured quads to be rendered off-screen if that's what we're using to actually show our images. So it goes ahead and turns back on the normal default frame buffer there, and then just kind of goes through and says, well, since I'm using a different frame buffer here, make sure to clear the depth buffer and so on. And here's a new one, GL draw buffer. That means draw the front buffer. So I think we just left that to its default before. You can do things like tell it to not draw the frame at all. You can say GL draw buffer none, and it wouldn't even bother drawing the screen. But in our case, we want to have it draw. As you get into generating depth maps, you might turn off your drawing altogether if you don't want that to happen. All right. So the extra bits here is that in the case of drawing to a textured quad, I added some code where, just so I could use my old shaders, get them to kind of work the right way, I did need to kind of zero out or basically set my any transformation matrices that I had set for my my model, my perspective, and all that kind of stuff. I just initialized them or reset them to be just identity matrices, and then I basically render out my quads if I need to, or they wind up in draw IMGUI. In the object, the image control here, so if we looked up in our, again, in IMGUI, we now have this if off-screen draw that texture color buffer as an image, right? So not a huge number of things changed, but a lot of bang for the buck there, right? So there's one example of using off-screen textures or off-screen buffers. All right. Now, let's go back to our content today, and we'll go to our lecture notes, and we have shadow mapping. I'll go through this relatively quickly. We'll see where we get. Like I mentioned last time, shadow mapping, implementing shadows, definitely the sort of thing is if you're generating your own engine, you're building your own engine from scratch or something, you're going to want to have, you know about implementing shadows. If instead you're doing graphics in a game that's in an engine, you're probably going to be more concerned with how can you cleverly use things like some of the other advanced shader techniques I'll talk about. So we'll go through this sort of a lightweight version of it, but we will still go through it. So if you want to implement your own shadows, you certainly can from here. I plan on providing some sample code certainly before the end of the semester. That'll do it. So shadow mapping is all about what the light hits. The importance of lighting and shadows, right? The big question here in this simple image, the big question is, of course, is the torus on the ground? How do you tell? It's hard to tell without any shadows, right? If we had shadows, we could say, okay, the torus on the left is on the ground, the torus on the right is in the air because of the way we see the shadows sort of below it. There's a very different visual impact there. We kind of see what's going on. So shadows can be very, very important. The nice thing about shadows is generally the way they're implemented is a separate rendering pass, which is why we don't have to normally, in Unity, we have exponentially more types of materials and shaders if you had something that's casting shadows or not, have a different shader for that. It's like, well, it really is part of it rendering the scene and then being a little bit simplified, but there are ways to kind of deal with that. right? So this is all about sort of how objects interact with one another, kind of. Geometry really has no idea what else is in the frame. Has no idea what else is in the frame, right? Lighting does have an impact on appearance, but shines directly through things. Nothing is occluded except by line of sight and depth, right? We use what's called a painter algorithm, basically, as things are normally drawn. We just draw things on top of other things, and that's, how the last thing out, the thing closest to the viewer, they see that because it's just drawn on top of potentially anything else. So as we're drawing, we're really kind of just thinking, all right, how is this particular fragment, what's the relationship between this particular fragment and the light? It has no idea of objects that are potentially in between it. So lighting has an impact on appearance, but generally shines directly through things. But the question now is, how can we take advantage of that and still provide shadows? In full screen mode, my bullets look really huge. So normally we only render what we can see. So we have the buffer, on-screen buffer, what is closest to the camera with regards to basically the depth buffer. Now to do shadows, the secret is, instead of considering what the camera sees, let's consider what is not seen by a light in the scene. Right? So we render from the light's perspective, and we generate a depth buffer according to the distance from the light instead of from the camera. Anything the light doesn't see basically becomes in shadow because it's behind something else. So when it comes time to render the scene, we can see, okay, how far into the scene is this fragment? Compare that to the thing that actually was closest to the light. And if it's not the thing that was closest to the light from that perspective, it's in shadow. Right? So it's a multi-pass process. The first pass renders the scene from the light's position. The depth buffer then contains for each pixel that distance. You copy that into some separate buffer, or you render it to a separate buffer, normally called a shadow buffer. The second pass, you render the scene normally, except for each pixel in its shader, you look up a corresponding position in the shadow buffer, and if the distance to the point being rendered is greater than that, the object is seen. Right? The object being drawn at this pixel is further from the light than the other way around. Let's see. If the distance to the point being rendered is greater than the value retrieved from the shadow buffer, the object, if it's further away, that means that there's an object between it and the light. So the object being drawn at this pixel is further from the light than the object nearest to the light. Therefore, the pixel is in shadow. So you need to make the pixel darker. Otherwise, draw it as normal. So pass 1, pretty simple. Pass 2 involves now using a shadow texture. Now, thankfully, OpenGL does have some support for shadow textures in the form of a sampler 2D shadow type. That will come in handy, but is not entirely necessary to implement shadows. You'll see different versions that do or don't use that. So here's sort of the step-by-step process, right? If you wanted to, not quite pseudocode, but we set up our buffers, set up a shadow texture, disable the color output, right? If we don't actually want to draw anything on the screen, we can disable the output of color. Anything you can disable in your shader makes the shader run faster. So if you know you're only going to be using your depth, well, go ahead, disable color output. You need to generate a look at matrix from the light to the objects in the scene as opposed to the view matrix of the camera. And then for each object drawn, you have basically a shadow MVP, or model view projection matrix, that is from the light's perspective. And you just call GL draw arrays as you normally do, right? You don't need to worry about textures. You don't need to worry about lighting because, well, other than the lighting of the depth here at this point, right? You don't need to worry about textures because you're not doing any drawing, really. You're not lighting things. You're really just looking for occlusion, right? The fragment shader doesn't really do anything because we aren't drawing anything in pass 1, right? So this is the sort of simple shaders we need in here, right? It's just basically transform things according to the position that the camera sees them, that the light, quote unquote, sees them from, and the fragment shader doesn't really need to do anything. If you do want, however, to kind of see what's going on, you can use the fragment shader and kind of draw things to get an actual view from the light's perspective. So what we have on the left here is sort of the normal scene, and the red version, if we actually rendered from the light's perspective and just made everything that the light sees red, that's what it would wind up looking. You can imagine, right, our pyramid now winds up, we're kind of looking through there, which is why it looks kind of square, because it has no shading or anything like that. And we get the torus there as well. All right. So depending on how you do this, if you want to actually explicitly create a buffer and then copy the buffer, you can do that sort of thing. You can copy textures around. Generally frowned upon, because anytime you're copying large chunks of data around, it's not very efficient. So one approach is that you can generate an empty shadow texture and use GL copy text image 2D and copy things into that. Another approach, the faster one, is to use a custom frame buffer in Pass 1, then attach the shadow texture with the GL frame buffer texture. Right? So you generate it on the fly, and then you can just use that. You never get it back at the CPU, because the CPU really doesn't care about it. We're only going to be using that shadow map in our shaders. Right? So the CPU never needs to know anything about it. That's why we can just say, okay, it's over there on the card, and so on. Don't worry about it. Now, in the case of using GL copy text image 2D, sometimes we're doing textures to textures on the card. It won't bother reading it back to the CPU either, but you don't have to worry about, at least, the overhead of copying things, moving things around, even on the GPU side. All right. Now, one of the things you do need to do in Pass 2 is you need to have some way of saying, well, what is the relationship of the text of the depth buffer to the actual image, right? Because you're obviously looking at it from a different perspective. So there is a correction that you need to do, or another transformation that you need to do, which is that matrix transformation for converting from light space to texture space, right? So when we look up things in the texture, we're looking up them in the right spot. So here we are creating a shadow model view projection buffer, translating, let's see, we translate by half, scale by half to change the light coordinates from a range of -1 to +1 to a range of 0 to 1. That's another piece. Right, so this way we don't wind up with negative values. It's easier to say something at 0 is going to be entirely dark, 1 is entirely lit, that sort of thing, as opposed to then having to say, well, what does -1 mean? We don't have negative intensity or negative light. So it kind of builds that in as well. All right. And here would be the process. Right. Build our transform from light to texture space, enable the shadow texture to be looked up in, enable the color output, enable our shader Pass 2 rendering program, use the appropriate matrices, and everything is, pretty much as usual at this point, except we have the little extra bit in the shader to say, well, is it actually shaded, right? So here's the other bit of magic. Vertex shader, pretty much normal. Converts vertex positions from model space to projected coordinates in the light's point of view, sends the results to the resulting coordinates to the fragment shader and a vertex attribute so they can be interpolated. Right? So it does have the light's position. The fragment shader calls the texture projection, which returns 0 or 1, indicating whether or not the pixel is in shadow, because we scaled it as we did in the previous slide. If it's in shadow, the shader darkens the pixel. If not, it's normal. Right? We even have some built-in things, right? So this is really what's going on. Beating this horse into the ground now, right? You can then look up in your texture shader, your shadow texture to see, is the corresponding value in the light or in the dark. Some reference codes, so as you're looking through the tutorials and whatnot, if you want to go here, see kind of some pseudocode version of that, it is available. I wouldn't use it word for word, but if you get to some point where you're like, well, it's not quite working, what am I missing? Kind of use this as a kind of a sanity check to look through the type of things in terms of binding the frame buffer, setting the right textures, all those sorts of things that you need to do. All right, so that's there. And this is the result. So things to worry about. It's an ideal world. You think, hey, look, it's all going to be great. And of course, your first pass tends to wind up looking way more crappy than you think, than you were hoping. Right? You do see the shadow. Hopefully on this slide you can see that there is a shadow of the pyramid over here. But you're also seeing all this ugly, kind of moire patterned, weird things going on. And this is typically called shadow acne or erroneous self-shadowing, right? Where a surface basically, because of rounding or because of inaccuracy, it thinks it is shadowing itself. Right? So the surface itself, the calculation was very, very close, but sometimes it's closer, sometimes it's off, so it thinks it's behind itself due to just inaccuracies. So you can wind up with that happening. Because it's such a common thing, there are a bunch of common approaches that you can use to combat it. One of the main things is to basically use something called the GL polygon offset fill. Turn that on and off, which basically gives it a tiny offset of the polygons being rendered so that they are slightly further away from the camera, or at least with regards to the calculation, to kind of push you past any particular boundary for that self-shadowing to fix itself. Right? So you're basically rendering your first pass slightly deeper than it really is. And that says, okay, things that are on the surface are obviously different, right? The surfaces will be in front of themselves because they're pushed by that offset. Right? There's another artifact called Peter Panning. Has everyone seen the Peter Pan, original Peter Pan film? One of the plot points in Peter Pan, or I don't know if it's much of a plot point, but at some point Peter's shadow, Peter is what is Peter? It's not an elf or something. I don't know. Peter Pan is this wonderful, he can fly, he can do all kinds of great things. But at one point Peter's shadow tears loose from him. And they have to capture his shadow and stitch it back to his feet so that his shadow is where it should be. So that's why this is known as the Peter Panning effect. And basically, there are situations where there's a shadow, but there winds up being sort of disconnected pieces of it because of, again, kind of rounding and other issues. Right? So you wind up with things seemingly not attached, or like when things should be anchored to the ground, they're slightly offset, things like that. Right? Sometimes there also are other artifacts like inadequate resolution of our our depth buffer. Right? So our depth buffer, because it's from a different angle and the light is a different distance and so on, how big we decide to make our depth buffers, our textures and so on, they are going to have different resolutions potentially than the images that are seen by the camera. So sometimes that will cause jagged edges due to the inadequate resolution of our depth map. All right, so that's another thing to watch out for. If you want to, this is a extra credit solving Peter Panning, solving jaggedness in your buffers, beyond the typical sample code that you find. Right? So that's the basics of shadow, some of the basics of the type of artifacts you see through the kind of the naive implementations, the simple implementations. Those are typically hard shadows, though. Right? Shadows, you're either in shadow or you're not. Right? So you wind up with hard edges on your shadows. Soft shadows, the shadows that occur in nature are typically soft shadows because we have all kinds of things like, not just occlusion, we have ambient lighting, we have global illumination, we have light bouncing all over the place, all sorts of wonderful stuff. And wouldn't it be nice for us to have some way to more easily, algorithmically generate soft shadows than really modeling light? So like so much of what we see, we're basically playing tricks. And with a lot of soft shadowing, what we typically are using is something called percentage close filtering, or basically filtering at the edge of the shadow to say, well, the closer you are to the actual edge of the shadow, you should do some, you can think of it as sort of like an anti-aliasing step, right? A blurring of the line at the shadow. The concept is simply to lighten or darken the pixels based on how many neighboring pixels are in the shadow. Right, so if all of the neighboring pixels are shadowed and this one somehow was not, well, there's like a pinhole of light that got through. We'd want to shade that, so that would get darker, right? If it's right along an edge, then we get something more akin to a simple filtering effect, right? So the more neighboring pixels that are dark, that are in shadow, the more the current pixel should be shadowed. That's a really cool technique. You see this, in this example, this shadowing looks really, really good, nice, soft. It is generated by sampling 64 neighbor pixels for each pixel being rendered. So it's an 8 by 8 block of pixels that it actually looks at and says, all right, for this one pixel, let me sample 64 pixels to see, is this really, how shadowed should this be? As you can imagine, that gets expensive. So depending on your graphics card and so on, you might want to do things that are a little bit more optimized. So we often do things like subsampling or dithering. So if we want to generate soft shadows, because of that sampling affecting performance, might use something like dithering. And what we mean by dithering is that you look for a certain number of pixels around in a sort of moving pattern. So when dithering, a smaller representative number of neighbors are sampled, and the selection of neighbors alternates depending on the location of the pixel rendered, right? So dithering typically is either dithering over time or dithering over spatially here. So we're sampling differently depending on the way the pixel is, so that we don't have something that winds up just looking like a lower resolution, right? If we always use the same exact reference, we'd wind up with something that just looked like a smaller resolution. Whereas with dithering, we can kind of simulate the higher resolution by having this moving pattern, right? So you see here we're sampling neighbors that are a little higher to the left, now lower to the left, upper to the right, lower to the right, according to that actual location, right? We're using this mod to figure out where it is kind of globally to figure out where things are. Right. And that type of PCF generally does a pretty good job. It's also going to be depending on your resolution. So a high resolution image with PCF filtering with just sampling 4 neighboring pixels is probably going to look pretty good, right? The higher the resolution of your image, the less you need to, the better the results of something that relies on just dithering can have. So it's kind of an extra bang for the buck with high resolution images, especially because you wind up with a lot of pixels in those images. And dithering itself works pretty well, and high resolution, it kind of masks the dithering effect also, right? So this is at the same resolution as our other image was, but you can imagine if we're suddenly able to do something that was the image itself was double the resolution, then our dithering would become that less pronounced here as well, right? So here is an example, a little bit of an example on that. See, the end result is pretty good. Now, that's the basics of shadowing 101 in OpenGL. These techniques are used for creating dynamic shadows, right? They are continuously calculated in real time, right? Every frame, everything's from a different perspective. You're generating the whole frame, you're generating the depth map, et cetera, et cetera, et cetera. So anything can be shading anything. It's very dynamic, and so on. In a lot of games, not every light is dynamic. Not every position of something is dynamic. You can imagine, the relationship between this object, the floor, and the light in the scene may not change over the course of time, and it's just in the background. Can the player ever get there? Does it really need to, is it ever going to be occluded? And as it rotates around, does that really change? The relationship of the light and the object and so on, even if you're looking at it from a different angle, the relationship between the light and the shadow really doesn't change. The shadow doesn't move depending on the viewer necessarily. So we can do things that allow for kind of compelling light and shadows and so on that are not dynamic. They can be baked in, right? I've heard that term, baked shadows in lighting, where we'll do some sort of calculation, maybe even in your authoring tool, to say, well, okay, let me generate a texture that goes on that object that represents the shadow of a certain light on that object. Right? So it would always make the texture of that object darker because it's not seen by that light. And then if something passes between that light and the texture, well, maybe it makes it extra dark, but it's only because, say, the player object was in that area that we really needed to calculate it. Right? So you can get smart about saying, well, okay, when a dynamic element suddenly is part of that scene, well, then maybe we need to use a combination of what we've pre-calculated or pre-baked plus some dynamic elements. Right? So you can do that, create the necessary maps beforehand, use texture lookup to avoid calculations. You are sometimes sacrificing dynamics for accuracy because potentially your baked shadows, you could do things with 64-bit dithering or 64-bit subsampling or really nice soft shadows. Right? So if it's not dynamic, we no longer need to make that sacrifice. We can calculate it based on 64 surrounding pixels because we only did it in Blender when we were baking the shadow maps, right? So you can actually have better accuracy of the things that you can pre-calculate. The nice thing is that you can compromise and use both, and light maps are supported by many tools. I mentioned, Blender can generate light maps, for example. I'm pretty sure Unity and Unreal both have, various baked lighting things that you can do inside of them, right? So not all shadows need to be dynamic. They don't need to be real time. We can rely on things like it's just kind of like our pre-rendered or our off-screen buffers, right? Imagine you just generated a light map for the scene, which is basically the depth buffer that you would have generated, right? So no longer you necessarily need to generate that whole depth buffer if you didn't want to. Right, so it's yet another way to use textures to help out, reduce the overhead of your scenes. All right. So that's our whirlwind tour of shadows. And next I'd like to talk about surface shading in general, right? More and more we start talking about, well, textures are doing more than just being bitmaps, and more, the sign on the wall, that decal sort of thing, right? We're doing more sophisticated things with textures. And even as you get into physically based rendering, which we'll talk about a little bit, but we'll just kind of gloss the surface of physically based rendering, if you'll pardon the pun, didn't even realize, gloss the surface. Even in the case of PBR, it does typically rely a lot more on different types of maps and different types of textures to tell you more about the physical qualities of certain surfaces. So to do physically based rendering, we need to take advantage of these things like off-screen buffers and different types of detail, different types of texture maps, and so on. All right, so it's important to kind of get the basic ideas for some of these things. So, surface shading, tricks for enhancing surface detail. Right, other ways to make sure that that fold in cloth, or that minor fold in cloth, or those dimples on a character, or that the crusty edges of brick kind of they're lit correctly. The embossed surface of paper has texture to it. You don't want to model every pixel, unless you're in the new Unreal 5 engine and you have a 3090 card and you're using nanites and all that kind of stuff. And even then, I'm sure they're doing lots of conversions for you to this sort of thing. Ways to do that sort of thing. So this chapter, or this piece of the lecture, used to be a chapter of the original textbook. But this section will focus on 3 related techniques. Procedural bump mapping. Whoops, why did I do that? Procedural bump mapping, normal mapping, and height mapping. And these all have to do with sort of either directly manipulating the kind of surface geometry, or more like it, kind of faking surface geometry as opposed to really manipulating surface geometry. There are all different ways to do it. Some of these names are a little bit flexible, fungible. You'll see sometimes talk about normal mapping versus bump mapping versus, let's see, somebody else had another term. It will occur to me in a minute. But don't get too confused if sometimes you'll see things, the names kind of shifting around a little bit as some of them wind up being combinations of other techniques and so on. Now, if you see a lot of new demonstration of these, you may also see this reference to geometry shading. We're not going to talk about geometry shading just yet, and how much we get into it we'll see. It's basically an OpenGL 4.0 sort of feature, so some graphics cards will or won't support it, but there are ways to kind of, I'll say this about geometry shaders and tessellation shaders and so on. There's ways for the GPU to increase the amount of geometry in a scene, basically to create vertices based on whatever technique you want to use. All right, so when we talk about geometry shaders, there are ways to actually emit or destroy new vertices in a model. Right? So you can imagine if we had some kind of really cool surface with a map and we said, oh, okay, let's generate that from scratch. You could generate new things using these geometry shaders, but we won't talk too much about them. If you see them in other examples, kind of put those to the side. Try to see just the bump mapping, normal mapping, and height mapping without geometry shaders for starters. So in the discussion of lighting, we saw that the normal of a surface helped us figure out, what the relationship between the light and the surface, how it affects the brightness of the surface, right? So we typically have had, say, one normal. Our model will have a normal per vertex. Sometimes it might even be just a normal per face, like in the case of a cube. You may wind up with them being repeated on every vertex because, well, okay, you're trying to define, flat shaded things. The cool thing that we had when we started doing different shading in our ADS model is we started interpolating those normals so that even our seemingly flat, very low poly objects, even though they were flat, they wound up looking shaded because their normals were being interpolated over their surfaces by the GPU for us. Right? So they wound up looking smooth shaded because they didn't have just a single normal for a whole face. We interpolated normals according to how things were oriented and their vertices normals. Right? So imagine if we were able to have a normal, not just at every vertex, but a normal at every, well, not necessarily at every fragment, but have a texture map that tells you the detail of the normals on the surface, right? So imagine we have, and these are just surfaces in general, right? Just a real surface, right? If we had a little bump on a surface, the normals along that bump would change, right? We have along the flat part of the geometry, the flat landscape there, our normals will point up. As we go up the curve and down up and down the bump, they start to point outward, right? They're sort of perturbed by that. So flat surface, they all face the same way. And the third case here is imagine that, well, we have a flat surface, but we have somehow made a map of what our normals would be. And we'll use that when it comes time to figure out how light interacts with things, right? So we have these perturbed normals that would be doing the right thing as if they were on a curved or bumped surface, right? That's what we call it bump mapping, because we're basically creating these normals according to where the bumps would be on our map, right? So we perturb the normal vectors to simulate surface bumps in the presence of lighting. So even with a flat surface, the behavior of light due to the normals creates this illusion of surface detail. We alter the normals at runtime with some procedure. We call it procedural bump mapping. So you don't necessarily have to have a texture. You can do something like this, where we have a sine curve that we're applying to this torus and generating normals according to mapping this sine curve to the model. So if you look carefully, you'll notice along these edges, it's still perfectly smooth. There is no actual bump in the geometry. But certainly the way the light hits it, especially where the highlights are here, it has that real feeling of kind of being wavy there. Looks like a cruller, I think. Is that kind of donut, a Krispy Kreme, kind of one of those donuts, sort of. So you could also, instead of perturbing the normals with a function, replace the normals using a lookup table. Right? So if you had a lookup table where we just say, all right, we have a normal stored in a texture, right? You could have normal maps for all sorts of different types of materials, right? Values in the normal maps are usually stored as offsets from a vertical relative to the plane. With the z coordinate set to 1.0, this is why normal maps appear bluish, in case you wanted to know that, bit of trivia. The surface tangent plane is defined by mutually perpendicular tangent and bitangent vectors. Okay, what is this piece about here? Both perpendicular to the normal. All right. So just having the normal isn't enough. We also want to figure out, okay, what would the tangent plane to an object be, right? That's normally, the normal is perpendicular to a tangent plane of a surface. So one way we can sort of simulate that, even though we don't necessarily have a tangent plane for every thing on here, is we can kind of simulate that by creating this, let's see. Oh, I think I have a slide for an actual image of the normal, bitangent, and tangent. So we'll get back to that. So here's using these two textures, these bump maps on a sphere, right? So there's no change in the actual image. There's only a change in how the light is reflected at those points, right? Pretty convincing, especially when you don't see it along a hard edge. Right here, if we look closely, it is completely smooth. We don't actually get that, this deep change in geometry there, right? But when it's just lit out front here, it looks pretty convincing, right? So one of the things we need to do, if you have a sphere, for example, you need to calculate the normals and the tangents. Here's an example of that being used. For some models, the tangents must be estimated based on neighboring vertex locations. We can do that. So the normal mapping, we're basically using, we're having a tangent vector, and we use a tangent and the normal to create, we can use the cross product of those two to create this binormal vector, which basically is an approximation of what our tangent plane would be, right? If we have at least one vector and the normal, we can cross those and get something that should be perpendicular to both, and that gives us approximation of what our tangent plane would be, so we know, all right, how would light be hitting that based on our new combination of things, right? So this TBN matrix we can generate, and then apply that to the values retrieved from the normal map to produce the perturbed normal. Right? So, some sample code here if you want to, as you go through. So imagine here we have the moon example where we have its texture and we have a normal map, or basically a bump map. Right? Sphere with the moon texture, sphere textured with the corresponding normal map, and then the effect on the moon. Now you can start to see, all right, here are changes in the surface that will be affected by the specular lighting, that will be affected by all the other lighting, right? That's the cool thing. Once you start normal mapping, then all of your other lighting can come into effect and change the particular output as well, right? So note the changes in specular highlights at the indicated locations. Now, it's funny, I always, in looking, I played a bunch of games since I first came across some of the images for these slides, and it still bothers me. A lot of them, there tend to be, if you naively do a lot of these things, bump mapping and modeling and so on, you tend to wind up, or maybe it's just a not really great choice of how the specular lighting and the way certain materials work. Everything starts to get this sort of really kind of greasy look to it. You ever notice that? Like there's a lot of, I'm going to say, certainly not AAA games, but a lot of walking simulator type games, a lot of more primitive games, or kind of single A, B level games. Their models, they try to get this all right. They use a lot of bump mapping and a lot of normal mapping, but they get the specularity wrong, and they wind up, it gives everything this kind of bizarre, greasy feel to it to me. I don't know. I'm playing Call of Cthulhu lately, and that's everything in there winds up just kind of being a little bit concerning in that. So be careful not to overdo specular lighting and finely textured surfaces using normal mapping and so on. Right. So combining texture maps and lighting with normal effects, you get some pretty convincing results. But remember, none of this actually changes the geometry. Right? So our edge is still perfectly smooth, but it can look very convincing, especially as it interacts with the light. Right. So the piece that the normal mapping or bump mapping doesn't tell you about at all is really the real geometry of the surface, how high, low it might be. It just tells you the direction of the normal. Now, so the next question would be, of course, well, what about using a map to tell you the real height of that position? Right? So you can imagine having a texture image to perturb the vertex locations. So you can use a grayscale image where a white value, a 1.0 value, is a high pixel, far from its original, and a black pixel is low, right, at the surface. So you could push things up and down. Now we can't just push fragments necessarily, but the first thing we might think is, well, maybe we could push the vertices. Right? There's no reason that you can't look up things and change vertex values using mapping as well. So if you have a sufficiently dense set of vertices, you could push vertices up and down according to some mapping. Right? So here's a height mapping in the vertex shader. Right? And we'll call your attention to this one, where we're just basically, if you're looking at the line towards the bottom here, vec4p, p is the vertex position altered by the height map. Right? We're adding an offset to the actual position, and we're recalculating the position, GL position, at that point. Right? The height map is grayscale. The color components we can use R dividing by 5 to adjust the height. Here, that just wound up being appropriate for their example. Right? But we're pushing vertices up and down on that map. So here's an example. If we did have a 100 by 100 rectangular grid, and we had a texture map for it, a height map for it, that is, we could say, okay, from that flat texture, offset each vertex, generate basically a terrain from that map. Right? This white box here maps to this white plateau over here. Everything is a fixed distance from there. So we moved all the vertices up. In these smoother areas, we created a sort of mountain range because they're kind of shading, moving up and down. Right? So it's a nice way to create a simple terrain just by having basically height map, right? Kind of a topological map. You can, of course, then combine that with other techniques. So we have a height map, a standard texture, and a normal map. We use that to create a world here with a certain precision, right? The challenge here is what should the precision be? If we don't have a geometry shader, we may need to generate a really dense mesh. But here you can see, in this case now, at the edges, we start off with a simple model of a sphere, and then we perturb the actual vertices so we do get real geometry at those points. Right? So this is one way to use maps, use texture maps or height maps along with the vertex shader. Right? The level of detail, ultimately using that sort of technique, is limited by the number of vertices in your model that you generate. Height map detail in between vertices is lost. Right? The rasterizer simply interpolates the height between vertices. The number of sphere vertices might be inadequate for using the moon texture. Yeah, remember that original moon texture, very, very high detail. But you wouldn't usually have a sphere that was that detailed. If you do have the capability, if your hardware does support geometry and tessellation shaders, you can help overcome that by actually generating the number of vertices as needed. Right? So if an object is far off in the distance, you can create very simple, you have a very simple sphere, and then the closer it gets, you can kind of crank up and change your geometry and apply textures and so on more interesting ways by having used geometry shaders, tessellation shaders. Right? And that is, wow, can't believe I went through that in that amount of time. That's the concepts for today, right? So the idea is always, what can we be using? What information can we be storing in textures? How can we use those in combination with our shaders, whether they be, simple vertex and fragment shaders, or ultimately as we start getting into geometry and tessellation shaders. But how can we change how they interact with light? How do we generate shadows and so on and so on? Right? So now you think about your projects, where you're at, where you want to be. If you've seen other examples, you want to entirely abandon your current project for the final project, feel free. If you want to make your project sort of the 2.0 version of your first project, that's cool too. So we'll talk about that. We'll have some, kind of more further presentations. I don't know if we'll have presentations, at least some sort of, boy, running out of oxygen today. Some sort of submittal based on, where you want to go, so we can kind of see, where you want to be in the long run here. It'd be nice to open it up to the class, since everybody will at that point have kind of seen everybody's projects and kind of can give people feedback on where they might be going, or suggestions that you can take or not take and so on. We'd like to kind of open it up that way. And look through here, and then also, if we want to refer back to our good friends at Learn OpenGL, my computer just Internet connection. All right. So we're here. We've done frame buffers. We've talked about cube maps. Advanced lighting is shadows in here. So if you want to see the shadow mapping section of Learn OpenGL, want to go through an actual step-by-step tutorial creating shadows. It does cover some solutions to the, let's see, shadow acne, as well as Peter panning. And even some oversampling to start to create some soft shadows. And PCF are percentage close filtering, right? So there's that. And it has, is that not dropping down? There we go. No? If you want a normal mapping tutorial based on that same code that everything is based on so far, just look at strictly normal mapping. They don't have a height map, but their normal mapping is, right? Here's that notion of having the normal, the tangent, and the bitangent, right? Allowing us to get, in this case, it's simple because it's just a square, since it's just a flat surface, right? And some cool results. All right. So we'll leave it there. Welcome back from your break. Polish up your project, publish some cool screen grabs from it. Think about where you want to take it next, and have a good week. Hopefully the weather won't be too miserable this week. We're for a lot of rain, I hear. So, okie doke. All right. Thanks for your attention today. And check out GitHub Copilot. I'm not advertising for it, but I think it is just, you know, I think it's going to be an important thing as far as computer science goes and the field careers and whatnot. Sort of going to have to be, everyone's going to be expected to know about it in some way, shape, or form, because we rely on things like, you know, coding interviews and those simple questions and so on to get jobs and to evaluate people and evaluate knowledge. I mean, I don't know what's going to happen with regards to how academically, and then we're going to deal with it, but it's another tool, another arrow in your quiver, I suppose, a really powerful one. Have a great day. That's it.